Hello. Welcome to the fourth module of the Python Fundamentals course, where we seek to understand the Python object model, take a more in-depth look at some collection types we've met already, and introduce a few more collection types. We've already talked about and used variables in Python, but what exactly is a variable? What's going on when we do something as straightforward as assigning an integer to a variable? In this case, Python creates an int object with a value of 1000, an object reference with the name x, and arranges for x to refer to the int 1000 object. If we now modify the value of x with another assignment, what does not happen is a change in the value of the integer object. Integer objects in Python are immutable and cannot be changed. In fact, what happens is that Python creates a new immutable integer object with the value 500 and redirects the x reference to point at the new object. We now have no way of reaching the int 1000 object, and the Python garbage collector will reclaim it at some point. When we assign from one variable to another, we're really assigning from one object reference to another object reference, so both references now refer to the same object. If we now reassign x, we have x referring to an int 3000 object and y referring to a separate int 500. And there is no work for the garbage collector to do, because all objects are reachable from live references. Let's dig a little deeper using the built-in id function, which returns an integer identifier which is unique and constant for the lifetime of the object. Let's rerun the previous experiment using id. Note that the id function is seldom used in production Python code. Its main use is in object model tutorials such as this one and as a debugging tool. Much more commonly used in the id function is the is operator, which tests for equality of identity. That is, it tests whether two references refer to the same object. We've already met the is operator earlier in the course when we tested for none. Even operations which seem naturally mutating in nature are not necessarily so. Consider the augmented assignment operator. Now let's look at that pictorially. We start with t referring to an int 5 object. Augmented assignment creates an int 2 without assigning a reference to it. It then adds the original int 5 with the new int 2 to produce a new int 7. Finally, it assigns t to the int 7 and the remaining ints are garbage collected. Python objects show this behavior for all types. The assignment operator only ever binds to names. It never copies an object by value. Let's look at another example using mutable objects, lists. We create a list object with 3 elements, binding the list object to a reference named r. Then assign r to a new reference s. When we modify the list referred to by s by changing the middle element, the r list has changed too, since the names s and r in fact refer to the same object. Let's see that again with a diagram. First we assign r to a new list. We then assign s to r, creating a new name for the existing list. If we modify s, we also modify r, because we're modifying the same underlying object. S is r is true, because both names refer to the same object. If you want to create an actual copy of an object, such as a list, other techniques must be used, which we'll look at later. It turns out that Python doesn't really have variables in the metaphorical sense of a box holding a value. It only has named references to objects, and the references behave more like labels which allow us to retrieve objects. That said, it's still common to talk about variables in Python. We will continue to do so, secure in the knowledge that you now understand what's really going on behind the scenes. Let's contrast that behavior with a test for value equality, or equivalence. We'll create 2 identical lists. Here we see that p and q refer to different objects, but that the objects they refer to have the same value. Of course, an object should always be equivalent to itself. Here's how that looks pictorially. We have 2 separate list objects, each with a single reference to it. The values contained in the objects are the same, that is, they are equivalent, or value equal, even though they have different identities. Value equality and identity are fundamentally different notions of equality, and it's important to keep them separate in your mind. It's also worth noting that value comparison is something that is defined programmatically. When you define types, you can control how that class determines value equality. In contrast, identity comparison is defined by the language, and you can't change that behavior. Let's look at how all of this relates to function arguments and return values. Let's define a function at the REPL which appends a value to a list and prints the modified list. First a list, and then a function modify which appends to and prints the list. The function accepts a single formal argument named k. We call modify, passing our list m as the actual argument, which indeed prints the modified list with 4 elements. But what does our list reference outside the function now refer to? The list referred to by m has been modified because it is the selfsame list referred to by k inside the function. When we pass an object reference to a function, we're essentially assigning from the actual argument reference, in this case m, to the formal argument reference, in this case k. As we have seen, assignment causes the reference being assigned to refer to the same object as the reference being assigned from. This is exactly what's going on here. If you want a function to modify a copy of an object, it's the responsibility of the function to do the copying. Let's look at another example. First, a new list, f, that refers to the 3 elements. Then a function which replaces the list, which we now call with the actual argument f. This is much as we'd expect. However, what's the value of f? F still refers to the original unmodified list. This time, the function did not modify the object that was passed in. What's going on? Well, the object reference named f was assigned to the formal argument named g, so g and f did indeed refer to the same object, just as in the previous example. However, on the first line of the function, we reassigned the reference g to point to a newly constructed list 17, 28, 45, so within the function the reference to the original 14, 23, 37 list was overwritten, although the unmodified object itself was still pointed to by the f reference outside the function. So we've seen that it's quite possible to modify the objects through function argument references, but also possible to rebind the argument reference to new values. If you wanted to change the contents of the list and have the changes seen outside the function, you could modify the contents of the list like this. And indeed the contents of f have been modified. Function arguments are transferred by what is called pass-by-object reference. This means that the value of the reference is copied into the function argument, not the value of the referred object. No objects are copied. The return statement uses the same pass-by-object reference semantics as function arguments. We can demonstrate this simply by writing a simple function which returns its only argument. Creating an object such as a list and passing it through this simple function returns the very same object we passed in, showing that no copies of the list were made. Now that we understand the distinction between object references and objects, we'll look at some more capabilities of function arguments. The formal function arguments specified when a function is defined with the def keyword are a comma-separated list of the argument names. These arguments can be made optional by providing default values. Consider a function which prints a simple banner to the console. This function takes 2 arguments, the second of which is provided with a default value, in this case a hyphen, in a literal string. When we define functions using default arguments, the parameters with default arguments must come after those without defaults, otherwise we will get a syntax error. Within the body of the function, we multiply our border string by the length of the message string. This shows how we can determine the number of items in a Python collection using the built-in len function, and secondly, how multiplying a string, in this case the single character string border, by an integer, results in a new string containing the original string repeated a number of times. We use that feature here to make a string equal in length to our message. We then print the full width border, the message, and the border again. When we call our banner function, we don't need to supply the border string because we provided a default value. However, if we do provide the optional argument, it is used. In production code, this function call is not particularly self-documenting. We can improve that situation by naming the border argument at the call site. In this case, the message string is called a positional argument and the border string a keyword argument. The actual positional arguments are matched up in sequence with the formal arguments, whereas the keyword arguments are matched by name. If we use keyword arguments for both of our parameters, we have the freedom to supply them in any order. Although, remember that all keyword arguments must be specified after the positional arguments. It's crucial to have an appreciation of exactly when the expression provided as a default argument value is evaluated, to avoid a common pitfall which frequently ensnares newcomers to Python. Let's examine this question closely using the Python standard library time module. We can easily get the time as a readable string by using the ctime function of the time module. Let's write a function which uses a value retrieved from ctime as a default argument value. So far so good, but notice what happens when you call showDefault again a few seconds later. And again. The displayed time never progresses. Recall how we said that def is a statement that when executed binds a function definition to a function name. Well, the default argument expressions are evaluated only once when the def statement is executed. Normally this causes no problems when the default is a simple immutable constant such as an integer or a string, but it can be a confusing trap for the unwary that usually shows up in the form of using mutable collections as argument defaults. Let's take a closer look. Consider the function which uses an empty list as a default argument. It accepts a menu, which will be a list of strings, appends the item spam to the list, and returns the modified menu. Let's create a simple breakfast of bacon and eggs, and naturally add spam to it. We'll do something similar for lunch. Nothing unexpected so far. But look what happens when you rely on the default argument by not passing an existing menu. When we append spam to an empty menu, we get just spam. Let's do that again. When we exercise the default the second time, we get 2 spams, and 3, and 4. What's happening here is that the empty list used for the default argument is created exactly once, when the def statement is executed. The first time we fall back on the default, this list has spam added to it. When we use the default the second time, the list still contains that item, and a second instance of spam is added to it, making 2, ad infinitum, or perhaps ad nauseum would be more appropriate. The solution to this is straightforward but perhaps not obvious. Always use immutable objects such as integers or strings for default values. Following this advice, we can solve this particular case by using the immutable none object as a sentinel. And now our add spam function works as expected. Programming languages can be distinguished by several characteristics, but one of the most important is the nature of their type systems. Python can be characterized as having a dynamic and strong type system. Let's investigate what that means. Dynamic typing means that the type of an object reference isn't resolved until the program is running and needn't be specified up front when the program is written. Take a look at this simple function for adding 2 objects. Nowhere in this definition do we mention any types. We can use add with integers, floats, strings, or indeed any type for which the addition operator has been defined. These examples illustrate the dynamism of the type system. The 2 arguments, a and b, of the add function can reference any type of object. The term strong type system is less rigorously defined than dynamic, but a common definition is that the language will not, in general, implicitly convert objects between types. The strength of the Python type system can be demonstrated by attempting to add types for which addition has not been defined, such as strings and floats. This produces a type error because Python will not, in general, perform implicit conversions between object types or otherwise attempt to coerce one type to another, the exception being the conversion to bool used for if statements and while loop predicates. As we have seen, no type declarations are necessary, and variables are essentially just untyped name bindings to objects. As such, they can be rebound or reassigned as often as necessary, even to objects of different types. But when we bind a name to an object, where is that binding stored? To answer that question, we must look at scopes and scoping rules in Python. There are 4 main types of scope in Python arranged in a hierarchy. Each scope is a context in which names are stored and in which they can be looked up. The 4 scopes, from narrowest to broadest, are local, those names defined inside the current function; enclosing, those names defined inside any and all enclosing functions. This scope isn't important for the contents of this Python Fundamentals course. Global, those names defined at the top level of a module. Each module brings with it a new global scope. And finally, built-in, those names built into the Python language through the special built-ins module. Together, these scopes comprise the LEGB rule. Names are looked up in the narrowest relevant context. It's important to note that scopes in Python do not correspond to the source code blocks as demarcated by indentation. For loops, with blocks, and the like do not introduce new nested scopes. Consider our words.py module. It contains the following global names: main, bound by the def main statement; sys, bound when sys is imported; double underscore name, provided by the Python runtime; URL open, bound from the URLlib request module; fetch words, bound by the def fetch words statement; and print items, bound by the def print items statement. Module scope name bindings are typically introduced by import statements and function or class definitions. It is possible to use other objects at module scope, and this is typically used for constants, although it can be used for variables. Within the fetch words function, we have the 6 local names: word, bound by the inner for loop; line words, bound by assignment; line, bound by the outer for loop; story words bound by assignment, URL bound by the formal function argument, and story bound by the with statement. Each of these is brought into existence at first use and continues to live within the function scope until the function completes, at which point the references will be destroyed. Very occasionally, we need to rebind a global name at module scope from within a function. Consider the following simple module. If we save this module in scopes.py, we can import it into the REPL for experimentation. When showCount is called, Python looks up the count name in the local namespace, L, doesn't find it, so looks in the next most outer namespace, in this case the global module namespace, G, where it finds the name count and prints the referred to object. Now we call setCount with a new value, and call showCount again. You might be surprised that showCount displays 0 after the call to setCount, so let's work through what's happening. When we call setCount, the assignment count equals C binds the object referred to by the formal argument C to a new name, count, in the innermost namespace context, which is the scope of the current function. No lookup is performed for the global count at module scope. We have created a new variable which shadows and thereby prevents access to the global of the same name. To avoid this situation, we need to instruct Python to consider use of the count name in the setCount function to resolve to the count in the module namespace. We can do this by using the global keyword. Let's modify setCount to do so. Quit and restart the Python interpreter and exercise our revised module, which now demonstrates the required behavior. Special cases aren't special enough to break the rules. We follow patterns, not to kill complexity, but to master it. As we have shown, all variables in Python are references to objects, even basic types such as integers. This thorough approach to object orientation is a strong theme in Python, and practically everything in Python is an object, including functions and modules. In Python, it's important to remember that everything is an object: primitive objects, functions, modules, and on and on. It's easy to see that when you start to explore even simple pieces of code. Let's go back to our words module and experiment with it further at the REPL. On this occasion, we'll import just the module. The import statement binds a module object to the name words in the current namespace. We can determine the type of any object by using the type built-in function. If we want to see the attributes of an object, we can use the dir built-in function in a Python interactive session to introspect an object. The dir function returns a sorted list of the module attributes, including the ones we defined, such as the function fetchWords, any imported names such as sys and URL open, and various special attributes delimited by double underscores, such as _name and _doc, which reveal the inner workings of Python. We can use the type function on any of these attributes to learn more about them. For instance, we can see that fetchWords is a function object. We can in turn call dir on the function to reveal its attributes, and we see that function objects have many special attributes to do with how Python functions are implemented behind the scenes. For now, we'll just look at a couple of simple attributes. As you might expect, this is the name of the function object as a string, and this is the docstring we provided. These give us some clues as to how the built-in help function might be implemented.